Hi, everyone. My name is Leo Jans, and I'm head of data engineering at Change Healthcare. Today, we're going to, first of all, I'd like to thank the organizers of this conference for inviting me, and I brought with me Ha Pham, an architect at Change Healthcare. And we're going to talk about healthcare data and the data-centric challenges that is facing us in our profession working with patient data. So before I go on, I just wanted to kind of give a little bit of introduction. So I have to first say one thing, that I love my job. I get to work on products that change healthcare, that actually changes and improves the care for patients. We work on products that have to do a lot of use cases, and they all have one thing in common. They actually improve the operations and the financial operation, and to make patient care better and more accessible to people. And that's why I really love this job. I just wanted to state that up front. I have some experience in this, and I just when people say what you do at work, I just ask them how much time do they have. So that's, I just want to state up front. And you can find my background on LinkedIn, but let's hit right to it. So why don't you introduce yourself quickly?
Hi everyone, my name is Ha Pham. I'm the principal architect at Change Healthcare AI Engineering. I had worked in building AI solutions for the healthcare for the last 6-7 years. I did have some experience on some other domain before that, but similar to Leo, I love the mission that we're doing, and I love the innovation in AI and big data and how we can apply those things for some real problem that we face here in America.
Thank you, Ha. All right, so healthcare data, it's messy for sure. This is 4 screenshots of de-identified charts that illustrates the mess we are dealing with. In our day-to-day job, we get patient data that consists of PDFs that have been, copied when people go out to your dermatologist and to your primary care provider, and takes photocopies of the charts and puts them all in a PDF, and then we use that in some use cases to extract diagnoses from there. We can do it to look at recommendations for treatments, how good quality the treatments are, and we can use it for pre-authorization and a bunch of other use cases. But let's just state up front that the data is messy. I think Andrew Ng started the discussion about data-centric AI a few months ago, and I think that that's certainly true for healthcare, where the data is not easy to label because it's very expensive, and it's not easy to parse and process because 80% of the information about me as a patient is in the notes that my provider, doctor, writes. It's not in my lab results, and not in my radiology images, and not in my prescriptions. 80% of the data that my providers have about me as a patient is stored in natural language. And so with the improvements and the great breakthroughs that we've had just in the last 5 or 6 years, starting with the transformers coming out and the LSTM and other modern techniques in deep learning, we're now finally able to start to what I call scratching the scratch of the surface about the possibilities of extracting information from natural language to improve patient care. And we're going to talk about some of the challenges and the solutions to these challenges in this session. So if you look at this, let's forget about the percentage for a minute. Let's look at like how it works, where we get data, we ingest the data, which is in some cases just a 400-page PDF, and then we use that data to infer different things such as diagnoses and such as conditions or treatments, and then we can predict different things there, whether this patient is a patient that actually is similar to a patient that has a approved knee replacement in the last 3 years, And then you can actually say that this would be a recommendation to approve this treatment or medication, for example. And then we present that to users. And the users, could be, a medical professional. It could be a provider, if it's clinical decision support, such a radiologist, for example. And or it could be someone that's working on payment processing and operations at a healthcare plan or a provider's group. And then in order to do all this, of course, we also have to have science models. We have to have, we have to have AI models that basically takes the profile of this patient and a condition, for example, and says, does Leo look like somebody that has a similar condition? Does, whether it's COPD or whatever it might be. And so that's the model development. And then if you look at the data, and we're going to go into more detail shortly, the data messiness that I showed in the first slide, just to get your ideas going here, is over half of the challenge. The 51% is the experience where we have the data legibility and the craziness about the data. And we're going to talk a little bit about how to solve that. And 22% has to do with models, and 10% has to do with users that may get presented data in such a way that they may make the wrong decisions. And I'm not talking about clinical decisions. Just like, you don't want the accounting system to turn in your taxes. We're not, at least in the role that both Ha and I have, working on clinical decisions, because that's really up to the doctor, because after all, the doctor has access to another feature, which is called the patient, which we don't. So I'm going to go into this a little bit more in detail. And Ha, why don't I turn it over to you to kind of describe the different classes of problems here a little bit in more detail.
Yeah, absolutely, Leo. And I will not go necessarily in the right order that we see on the screen here, but if one class of the problem that we face a lot when we analyze this medical document is what we call data legibilities. So because of the nature of the industries, we don't necessarily receive the document in structured data. In many cases, we receive this data that's been go to a fax machine, that's been copied a few times, that's been merged, from multiple systems, has different resolutions. So by the time it gets to us, one of the major challenges we have to be able to do OCR on this document and understand the text on this document. So example of issue that we face into are things like you misunderstand, even for a human, number 3 versus number 8, as an example, or number 1 versus a slash symbol, or letter J or letter L. These are major issue because when we are looking at the readings that's been written on the document, if we get the different reading for the BMI level, like instead of 11 you got 14, then you obviously will come to a different conclusion. This in itself is a very difficult problem, and as with anything else, if you have garbage in, you have a garbage out problem. So when we have data coming in, not necessarily garbage but very complex and can be blurry, we have a major issue here. So in our experiments, this class of the problem, the data legibility problems, they account for about 18%, 20% of the issue that we face in terms of the error that we run into. In medical document analysis, the understanding exactly what date the document belongs to is of utmost importance, because we need to attribute the treatments and the condition to the correct year. So because of that, this data legibility, especially around understanding the date on the document, is a major issue, because the whole lot of business rules will have to apply based on the date and the year, and this in itself is a major multiplier.
So let's dig into that a little bit more specifically. It seems simple with a date, but you can imagine a blood pressure screening for the condition of hypertension, high blood pressure, and you have a blood pressure screening where you don't get the blood pressure right because the numbers aren't correct. And B, you may not get the latest blood pressure reading. And so that's examples of where those dates and those numbers are really important.
Thank you, Leo. Then let's talk about a different class of problem that we face. That is on, the first line right there, data modality and negations. Essentially, in the text, in the doctor's note, there could be language and phrases that are ambiguous. So when we look at these things, either because of the doctor write in a certain manner, like, I sleep pretty good, as an example right there. But in many other cases, because of the way it's been written, we do not know whether what the intention is really behind the scenes. Leo, do you want to talk about an example in these situations?
Yeah, this is from an actual patient chart where the doctor asks this patient that comes in for heart palpitation, and so the heart beats a little bit, a couple times a week, and the patient is worried about that. And so the doctor asks the patient, "How are you sleeping?" And the patient answers, "I sleep pretty good." Well, the doctor actually doesn't write that in the chart. The doctor actually writes that the patient denies orthopnea. Orthopnea is a condition like sleep apnea, where you wake up after a couple hours of sleep because if your heart is weak, you get a little bit of water in your lungs. So you wake up kind of, I wake up. And so the doctor can by saying that I sleep pretty well, conclude that orthopnea is not one of the conditions. Orthopnea is one of the symptoms for cardiac disease. Now, when we see this sentence in a document and we go through this, the denies denominator is scoping only orthopnea, and there's a dot there that we have to catch. Because if we don't catch that dot, all of a sudden the patient denies no changes in sleep pattern. That means that the patient says, I have changes in sleep pattern, which actually would point to the condition orthopnea. So
Yeah,
this is an example where the dot is the difference between one conclusion and another conclusion.
I want to add something in there. We did some analysis in our team when we look at the resolutions of the documents that we receive, and the DPI, basically the how many pixels per square inch a document come in. It range widely from some document is at 50 DPI to all the way to like 1,000 DPI. So when you have that kind of range in DPI, the dot can be easily missed or added, without knowing. So that's why this problem multiplied by the fact that the data that we receive come from multiple sources that have been exported, maybe copied, maybe faxed over multiple mediums. That's what we're facing.
And the volume, the volume we're doing is roughly 750,000 patients a month, and each chart is average 230 pages, right? So you multiply that, and you have hundreds of millions of charts pages that we actually process. And so missing a dot on one of those pages is key. So we really have to watch. It's all about the details. What else, huh?
Yeah, so let's talk about the next class of the problem we're facing. This is to do with the fact that the document might have multiple tables or forms in the data. So very, very frequently you see medical form where they have, questionnaire, things like, asking the patient to circle in a certain spot. There's multiple column documents. This in itself, pose a huge challenge because when we receive this data, we don't necessarily have this information. And we have to decide when is it that this document have multiple document, multiple column versus when they don't. It vastly confuse the science model if we train the data without this kind of information. In the sentence that you read straight out, this thing, if you misunderstood it and think about it as a single column document, then you have a completely different meaning out of the text as you analyze it.
Good. And let's talk about the model specific errors that we've seen.
Yeah, absolutely. So model, when you build a model, the first step is you have to do model trainings, and then one kind of first wave of solution that people come up with is to use a set of dictionaries and phrases to do matching on this. And this is where we face a challenge of model training that have a dictionary mismatch. This is purely coming from the fact that the text can be written in many different ways. The dictionary might have misspell in them. There might be industry standard shorthands or hospital specific shorthands way of doing things that we do not know. So this in itself will pose a lot of challenge for the model to get it right. Next level is on the model labeling. Often people will try to account for the problem I just mentioned by hire some domain expert to help label the data. Even the domain expert themselves disagree among each other or perform differently on different days. So we have a situation where three experts can still disagree on what the conclusion should be or what the conclusion should be on a piece of data. This account for surprisingly 10% of the times.
How do you fix that? How do we fix the whole two or three experts look at a patient and says this patient does not have Alzheimer or this patient has Alzheimer?
Well, they're obviously relying on the labeler alone. Does not work. So in this case, we actually treat the labeler input as if it is a feature. So in a way, we understand and we study the historical data that's been provided by the labeler and use that as a feature into the model. So we don't, in another word, like we don't trust the labeler data, blindly. We trust that with a high degree of with some degree of uncertainty.
So if I'm hired as a subject matter expert and my specialty is certain diseases, say Alzheimer, for example, then will I be the only one who decides or who
No,
says?
so there are different ways to do this. So we could have things done in a way that we have multiple tier of labeler. So that way we have a more experienced labeler to act as a second phase review of the first labeler to give us a higher quality data. That's one way to do that. Another way is you allow a situation where you do a quorum, like two out of three need to agree with each other. That would give you a different way of getting the quality label. There's a techniques in manufacturing called statistical QA. In that sense, what they do is they check the accuracy of the labeler once in a while, and then increase the frequency of checking that if the labeler make mistake, or you have check that less frequent if the labeler make all the correct the decision along the line. So there, basically, you use a combination of different labeler and arrange that in different ways to give you higher quality label at the end of the day.
Right, right. Well, data labeling is one of those things. I remember, when we worked on a product some time ago, that I hadn't really thought about the labeling challenge. And I remember we were looking at a new product where we thought that we were going to have to spend about $1 million to do labeling, and we basically got 200,000 as a budget. And we looked at each other going like, wait a minute, how can we do this cheaper? I know there's a lot of work has been going on at Google to decrease the cost of labeling, and that's something that is often overseen. But you can imagine if you can actually make a dent into that percentage of errors by focusing on labeling. So back to the data-centric approach. Take a look at how you do labeling today, and you're only good as your label, because with deep learning and everything, like if you do a system that's going to recognize images of a dog, and you basically say that this dog is a poodle when it's actually a German Shepherd, obviously the system is going to be incorrect. It doesn't really matter what the mathematics is behind it. So that's another one. I'm going to show another slide here, and this is the last slide because of time. We have about 5 minutes left. And that kind of gives a potpourri of these solutions, right? And we talked a little bit about them. We talked around the OCR and the page classification that's required to make the data more legible, right? But why don't we, and we just finished talking a little bit about the labeling on the SMEs, and I do apologize if the slides are fairly unreadable, but with the color, at least for me. But anyways, I wanted to talk a little bit about the low precision and recall, the model performance class, which is kind of overarching of these. And first, let me just give a fifth grader definition of precision and recall. In the case of when we derive diagnostics, we actually do have a system that we developed from scratch at Change Healthcare that takes the patient data and determines the diagnosis of the patient. If you look at that, you want to find all the diagnoses, right? So every diagnosis is very important. and therefore you want to get high recall, right? And because the diagnosis, ultimately translates to revenue. So the way I remember recall is that it starts with RE, which is revenue. So if you go fishing in the ocean and you there's 100 tunas there you want, and you have 100% recall, that means you get all the tuna, right? So that's the recall. And the precision is how often you're right. And so if you are presenting things to a physician, you really want to be right a lot. You don't want to present to a physician, Leo may have this, he may have that, he may have this, and the physician spends half an hour to kind of, chase down what's going on. You want to really be right a lot. So how do you improve the precision and recall from a data perspective here, Ha?
Thank you, Leo, for that question. So this is related to the model performance, and there are so many techniques in looking at the data, improve the model performance, use different ways to improve that based on the data that you have. But what I want to mention here is we found that we want to use a different class of data that help you vastly in a different way. That is mainly to look at the bigger picture and the context of what's going on. So instead of only looking at the text about the patient, this medical document at hand, a lot of the thing can help you at the bigger context. So for example, if you look at the patient context as a whole and you see, whether this patient, what is the historical condition of this patient in the past year. The other thing that's also important is what we call the condition prevalence. For example, when you look at the older population, people who are 65 and over, there are about 5 or 6 conditions. Diabetes, heart-related conditions, lung-related conditions, a few of those things. Those things attribute for almost vast majority of all of the conditions that people have. So you can use that to your advantage. So you can boost the score of the detection if the detection relates to those conditions. And then along the same line of looking at prior history, looking at prior history of the patient is one way to do that. Another one is to look at the prior history of the doctor themselves, the providers, because if the provider know what they're doing, then likely that they make the right decision again. So if we can incorporate all these different dimensions of data that's beyond only the document that you look at, then you can make a much more educated kind of guide to your final classification. Essentially, you can dynamically decide where your cut threshold is in terms of the sensitivity of where do you pick up one of your predictions or not, and that will vastly improve your recall and precision.
So in practice, then, I mean, we are processing, as I said, we're going to be probably close to 1 billion pages here in the next few months. And which maybe 4 million patients, 5 million patients. And if you look at that, you would assume that if we have a batch of 100,000 retired people in the US, that you would end up finding that 17.4% plus minus something has COPD, for example, which is kind of like the prevalence. So how do you implement that? How would you know that? How do you explain a little bit how you go about validating that data?
Yeah, Leo. So in that situations, let's say that I am looking at a medical document of one patient in front of me, and I have some scoring that I think potentially this patient has COPD. The one way to do this thing is you can set the threshold in a way that's fixed, but another way that you can do it in a dynamic manner is you take into account how prevalent is this condition for this patient populations, and then use that to dynamically adjust the threshold accordingly. So in this example, if the patient falls into the category of the group who has high prevalence for COPD, then we can afford to accept the prediction that might have lower confidence score if you only based on the text in front of you. So an older patient, if you have a 0.2 confidence score for COPD, you might accept that prediction. Whereas for a different patient who belong to different population altogether, you might require the confidence score for COPD detection to be higher. So by taking advantage of the prevalence of this condition for the population that you're dealing with, you can make an informed decision about the the threshold tuning, and that gives you that advantage in getting that extra last mile of recall and precision.
Yeah, no, and I think also that is another way that we don't have time to cover here, which is how you can correct biases, right? Because some conditions are much more prevalent among an older population than a younger, or vice versa, for example. And you can actually use these type of thresholds to correct for the fact that you may have a lower prevalence of a condition in a certain age group. So this is where the post-prediction processing and data engineering is important. That adds things to just inferences that the science model does. And that's what I wanted to cover, that we wanted to cover today. I hope that this gives people some ideas. And it's all about the data. It's really all about the data. And I know that there's a lot of startups out there that are talking about data validation, and it's really important to have a look at the data quality here, from when we get it, from when we label it, and the data quality of the output as well, right? So with that, I want to thank you, Ha, for participating in this session. And again, thank you to the conference folks for inviting us to come and talk about this subject, which we love. Thank you so much, and have a great rest of the day.